Okay, everyone. I hope you can see me, you can hear me, and you can see my slide deck. So thank you for joining on this 5th of January, which will be probably one of the first webinars of this year. So let me wish you a very pleasant, healthy 2021, and a safe one, of course. And besides all the good stuff, I wish you a lot of Kubernetes, containers, and security. So to kick off this year, we'll start at a lower level. Today, we will discuss about kube-proxy and how Kubernetes actually manages Kubernetes services like cluster IP, node port, and load balancers. In exactly 2 weeks from now, there will be an add-on to this webinar where we will discuss ingress routing, which is also a very cool topic to discuss. So let's kick off. Also on this call is Jane. She's my colleague based in the UK, myself, Philip, and I'm based in Belgium. And click. So if you want to check us out, go to LinkedIn, Twitter, whatever, and you can find me. So Calico, as you probably know, is a community-driven project backed up by Tigera, which is a company behind it, and focuses on open source networking, one of the most widely used open source networking solutions in Kubernetes, but also as well a security solution, because Calico was one of the first and also most advanced network security policy solutions there is around today for Kubernetes. Now, Calico runs in Kubernetes, as I mentioned, but you can also use it on a virtual machine running in Linux, or in a cloud, as well as to protect the Kubernetes nodes itself. So if you want to participate, go to projectcalico.org or join us on Twitter, go to Slack. There is a very large Slack community that can help you with the open source issues, troubles, or questions that you might have. So feel free to do that. So Calico, or Project Calico, is the open source version of the project. There's also an enterprise version, which extends and adds, of course, functionality on top of it. But just to put it in perspective, Project Calico is used almost everywhere. So you can find it in most managed cloud solutions, EKS, Google, Azure, IBM. All of them do implement the Calico networking policy functionality. Some of them also started to use the Calico CNI. You can, of course, also use it on native Linux and Kubernetes, on Docker, on Mirantis, OpenShift, Rancher, and so on and so forth. Not to forget, you can also use it on bare metal. This is the case in which we will use it today, although it's running in VMs. And last but not least, you can also use it on Microsoft. The enterprise version itself has a little more networking features and security features than the open source one. But important in this picture is it's also ready for multi-cloud, which means that you can have one central management plane that is actually managing all your Kubernetes clusters wherever they live, and giving you all the logging and visibility that you want. So let's dig into the networking part. So as you know, every Kubernetes cluster does need some kind of networking. That's how the pods are actually communicating. Kubernetes itself does not implement any kind of network. That's basically provided by what is called a CNI. Calico is a CNI, a container networking interface. So Kubernetes actually relies on a CNI. Of course, for this webinar, we'll be using Calico, more specifically Calico, the open source version. So whenever somebody tries to schedule a pod, and the pod is assigned to a node somewhere in the cluster, the node will try to obtain an IP address. And this is done by kubelet. And kubelet tries to obtain an IP address, which can be specific for each node. Once a pod has an IP address, well, it can actually connect, of course, and talk to the other pods. So that's one of the design criteria and things to keep in mind is that every pod inside of a Kubernetes cluster can talk to any other pod in a Kubernetes cluster without any need for address translation. So you can consider it one big flat network with no security. That's where the network security policies come in, of course. That will allow you to basically filter on who can communicate to who. But some CNIs simply do not implement network policies. Now, another things which complicate things and will also basically decide what we're going to do with the cluster IPs and the kube-proxy stuff is that pods are scheduled somewhere on a node and they are actually assigned one of the free IP addresses. So that also means that IP addresses cannot be predicted. So if a pod comes up or a pod is scaled out through means of a deployment or by a replica set, means that some pods will have different IP addresses. If another pod comes up an hour later, it might actually take that IP address if the pod does not exist anymore. So relying on IP addresses inside of Kubernetes is not a smart thing to do. And it will probably put you in a lot of issues later on. Last but not least, this is not always the case, but quite often the IP addresses used by pods are not routable or non-routable outside of the cluster. So quite often it's a range of IP addresses which is encapsulated or not encapsulated, depends on which CNI you're using. But very often, except a few exceptions, like for example in Azure, these pods are not reachable or cannot be routed outside of your cluster. That's why we actually need services being introduced later on. So as I mentioned, the CNI is basically the part that will assign IP addresses. You have very simple CNIs, like for example, host local. You have very more advanced CNIs, as for example, Calico, which can use multiple types of encapsulation or non-encapsulated mode. That means that you have no tunnels in between your nodes. And Calico also has a very extensive way to do IP address management by the use of IP pools, blocks, and so on and so forth. So that means that Calico can actually, in an intelligent way, assign IP addresses and manage the IP addresses. You don't need all that stuff for only 2 nodes, but once we start scaling to tens or hundreds of nodes and performance becomes an issue, well, good IP address management is crucial, and for sure also when we talk about allowing traffic from outside into the cluster. So take a look at the link and you will find way more information, or check out one of the other webinars, which are all on YouTube, by the way, to review. So to start out this exercise and this discussion, we first need a deployment. And we're probably all deployed already a deployment or an nginx pod, but there are a few things I need to point out. So once we deploy an application, this is a simple Nginx application, you can actually see that the container is based on the image, nothing abnormal, and that port 80 will be used. So that's basically the image we're going to use for our pods using container D, and for a few weeks Docker, we can use that image. Now, the pod itself has a label, and this is very important for services. So that means that every pod that we basically spin up, and we're actually spinning up 3 replicas, that means there will be 3 pods running somewhere on a node. As you can see in the picture, they will get an IP address out of the pod CIDR range. So that's the range that is assigned to give IP addresses to pods. You see 71, 122 here, 93. This is actually Calico, who actually assigned subsets to specific nodes to optimize the routing. But at the end of the day, everything is in 192.168/16, which is the pod CIDR. So the replicas defines how many pods we have. Every pod has a label called app Nginx. That means that you can identify all these Nginx pods if you search for a label called app Nginx. Yeah. Sorry, this is the labels assigned, and the deployment basically checks for these labels. Okay, so we have labels. By means of labels, we can actually select pods, and that's how we can actually make sure that we have 3 replicas available. This does nothing more than just spin up 3 versions of Nginx somewhere on a Kubernetes cluster. To show you then dynamic IP addresses, while, for example, if you would scale up your replica set to 5, yeah, 2 other pods will spin up. They will get an IP address from the CNI, and they will be reachable. So you should ask the question at this point, yeah, right, but if the IP addresses are dynamic, how does an application, how does an external client, how does a web browser actually knows to connect to which IP address? Yeah? What happens if the pod disappears? I need to connect to another one. Well, that's where clustering and kube-proxy comes in. So this to prove the fact that pods don't live forever and IP addresses do change. If a pod fails, like in this scenario, the fact that we have a declaration or a declarative form of a service, like a deployment, yeah, automatically a new pod will be scaled up when the other one dies or is killed. So keep that in mind. So it's dynamic. We have no idea actually to connect to which pod. So Kubernetes basically solves this by the idea of Kubernetes services. So a Kubernetes service is a Kubernetes object, like pod is an object, like a deployment is an object. Well, there is also an object or a resource called service, and it's actually a collection of pods. So a service is nothing more than an object that links together all the pods based on a selector. So if I want to create a service, I could say, okay, this service is representing all the pods with, for example, app equals Nginx. Yeah. The service is actually accessible on what is called a service IP address. Yeah. So in Kubernetes, there are 2 IP address ranges. One IP address range, pod CIDR, is used to assign IP addresses to pods, but a very important one is also the service CIDR. The service CIDR is actually a different, actually a non-existing network range that represents that logical set of pods. I'll show it in an image right away, how it works. So through the means of services, we can actually decouple or make an abstraction of where the pods live. So if you connect to the service, Kubernetes will make sure that you get connected to a pod that is actually alive. Yeah. It's also used for service discovery, because just imagine two pods that need to connect. For example, Node.js needs to talk to whatever Redis. Yeah, since pods are dynamic, you cannot configure one pod to connect to the other pod if everything is dynamic. So service discovery here is actually a way to find out how to reach another service. Quite often, it's not any more complicated than DNS. But services do allow to do this. So it would be easy and fast if there was only one simple service, but there are multiple types of service. The most common one, or the most used one, or the most implicitly used one is a service type called cluster IP. You don't see any type here, but you could actually say type cluster IP. But by default, it is cluster IP. So essentially what it does, it gives the service a name, in this case, my Nginx cluster IP. The service basically hosts port 80 on TCP, and it actually groups together all the pods with labels app Nginx. So if I take the example I just had, where my pods are essentially on different nodes, yeah, we're now going to think away the nodes, but just remember that pod 1, pod 2, pod 3 can be essentially everywhere inside the Kubernetes cluster. The pods still have their IP addresses assigned by the Calico CNI in this case. And when we define actually the cluster IP address, well, you can see that there is a other strange IP address, a service IP address, is actually the IP address that will abstract the services. So that means that if you can connect to, in this case, 10.104.59.110 in some way or the other, yeah, you will be intercepted by IP tables. I'll talk about that later. And IP tables will make sure that you get directed to one or the other pod. This is, in brief and very short, how kube-proxy works. So once you define a service, yeah, kube-proxy will actually program IP tables on the Kubernetes nodes to make sure that if somebody connects to the service IP address, gets directed to one or the other pods. If something changes, kubelet gets aware, it will remove it. Kube-proxy will make sure that finally the pod is removed from that service and deprogrammed actually from IP tables. So that's the most simplest case. Now, every service, once you define it, also gets a DNS name. So that means once you define a service, like for in this case, my Nginx cluster IP, well, you can actually reach that one without knowing the IP address if you connect with a host name like my Nginx cluster IP. This works fine as long as you're in the same namespace, but cluster IPs are reachable outside of the namespace they're programmed in. So that means that my Nginx cluster IP also has a host name like my Nginx cluster IP, my namespace service.cluster.local. So if you connect to this name from anywhere in the cluster, you will essentially and finally come to this one of these spots. It's easy to troubleshoot. And as you can see, you only have to know the name don't have to know the service IP address nor the pod IP address to connect. Pods by default don't have a service IP. Pods by default don't have a host name by default, which is in DNS.
Philippe, we have quite a few questions in the Q&A which are open, which I can't answer. I don't know if you can take them now or there's a good time to take them.
I cannot see the Q&A for one reason or the other.
Do you want to read them out? Let me know.
1 second, I'll see if I can see Q&A section. This is DNet in IP tables. Yes. We'll see it right away. Does Calico assign a /24 for each node? By default, it can, but it's configurable. Yeah. So you have the pod sider. Actually, Calico creates an IP pool from the pod sider, which by default is /16. And from each IP pool, it will create a block per node, which is /24. But it's configurable, but you're correct. What about applications which require persistence? That's a very good question. There are other types of load balancing mechanisms, which we do not cover, but there are ones that you can use, for example, headless or pure on DNS name. And if you really need persistence, you can use a kind of proxy like Nginx, Traffic, or whatever. This is more related to ingress. But in this case, where IP tables doesn't do persistence by default. Yeah. Okay, single pod to internet with different subnets. Technically, with pods you cannot do that, but you can use something like Multus, and Multus can actually use two different kind of CNIs, 2 interfaces, or I guess even 3 interfaces, and so on and so forth. But check out Multus. Can we support up to 5,000 nodes? I've never checked, but according to our documentation, we can support up to 10,000 nodes, if I'm not mistaken. So I never made a calculation, but technically it should be possible. Now, 3 million containers or 300, I don't know, 150 pods or should be possible. Just take in mind that typically you don't have the ability to have so much pods on one node. So typically you would count around 100 or 150 per node, but should be technically possible, I guess. And how are IPs assigned to pods? Well, the moment a pod is scheduled to a node, this happens on the Kubernetes master, kubelet will basically see that it has to schedule a node, and it will actually use a binary to actually communicate. And I think, let me see here. I don't know if I have it in the slides here. I removed it, but there is actually a directory on a node, which is a CNI, which is, here it is, typically in CNI bin, where an executable is installed, and that executable will make sure that an IP address is assigned and so on and so forth. But that executable has a CNI interface and is provided by Calico or Flannel or whatever you are using. Okay, so the cluster IP address, So as I mentioned, is used from the cluster range, cluster IP range, so the service side, and quite often is not reachable from the internet, from outside or from the internet, of course, except if you use Calico, you can do that. Now, this is typically used for inter-cluster or in-cluster communications to make sure that microservices can talk to other microservices. There is an exception with Calico, which makes it more broader, but let's say in general, this is the case. Something interesting to know is that there is also a service of type node port. And type node port is actually a service definition. But by specifying type node port, what you actually do is make sure that the service we just created, so that IP address port 80, is actually exposed on every node. Yeah, so remember pod 1, 2, 3, we're sitting on node 1, 2, 3. So every node, the moment you specify node port, will open a port, in this case 3970. It's always something in the range of 30,000 something. So the moment you actually create a service of type node port, it will actually create the cluster IP, but it will also make sure that that cluster IP we just created is exposed on every node on the host node IP address. So that means that if you connect to the Kubernetes node on this higher port number, you can actually reach the service. That means if you have 3 nodes, if you look from the outside, every node will actually have port 30,970 open in this scenario. That means that no matter to what node you connect, you can actually reach to this port. You can fix that port to a number in the 30,000 range, but just keep in mind that if you delete and recreate a new one, the port number will probably change. So I'm not saying it's totally random, but it's hard to predict what that number will be. But remember, node ports are used quite a lot. And that's how, for example, if you use kubectl, kubectl connects to the kubeAPI server. Okay. The last one is even more advanced. The last one, there are a few other types of services, honestly, but the last one we discuss is the one of type load balancer. Type load balancer will create a load balancer, but keep in mind, Kubernetes does not provide a load balancer. Type load balancer is actually an external load balancer. Now, this is easily used inside of managed clouds. If you go to Azure or you go to AWS, if you go to DigitalOcean, if you go to IBM Cloud, probably, the moment you actually define something like this, it will do actually the stuff we just discussed. It will create a cluster IP address. It will actually create a node port, and then it will actually talk to the load balancer. Most of the time, this is through an API to which you can connect or talk to the cloud provider. So the moment you do that, your Kubernetes cluster, for example, EKS, will talk to AWS API and actually instruct the AWS API to spin up a load balancer. So by typing kubectl, apply something like this, your Kubernetes cluster needs to be able to talk to the cloud provider or to the load balancer because it's implemented by means of a controller, and it will actually spin up a load balancer for you. That load balancer does not exist inside of Kubernetes. I'm not saying it cannot run there, I'm just saying it's not something that is owned by Kubernetes. So to make a very long story short, if you actually want to expose these Nginx pods and make them reachable outside of the internet, well, you actually create a load balancer, will create a cluster IP, will expose the cluster IPs on each node on the host. The load balancer will make sure that all incoming traffic, in this case, for port 8443 that hits the load balancer will be sent to one of the Kubernetes nodes. Yeah. When it reaches one of the Kubernetes nodes, IP tables will make sure that it actually reaches the correct pod. Okay. So I didn't spin up one in a cloud. I'm using for the demo right on the one in AWS, which I built myself. But if you do that, so the moment you actually create a type of load balancer, you will actually see, for example, I have a few examples here. So the first ones are actually the pods. You can see them. You can actually see the services. If you just create a service with cluster IP, it just has a cluster IP address. Yeah. If you create one of type load balancer, yeah, it actually gets an externally reachable IP address. If you do that, depending on the cloud you're using, it can take a few minutes. So if you do it and you check it, you probably see something like pending for a minute or 2 or 3 minutes until the load balancer is configured, and then you will actually see the public IP address. That's the IP address on which you can reach the load balancer, and he will make sure that you get it to the pods. When you define one by node port, you see, you actually see the node port IP address, so the 30,474 in this case, is actually available on every node on that port number. Yeah. Voilà. So these commands, we'll see them more in the demo. One thing to note is, because I actually said you have to use node port to make a service accessible on a node through means of a node port or a load balancer, depending on how much money you want to spend. With Calico, you can actually advertise. Calico is based on BGP in most cases. Calico can actually advertise the pod IP address into the network outside of Kubernetes. So basically, your Kubernetes can actually tell the upstream router saying, hey, these are the IP addresses for the pods I have. You can reach them routing-wise. That's one way to do that. But as I said, this is dynamic, so it doesn't make much sense. But you can also do it for service IP. So if you don't want to use node ports and you don't want to use a load balancer, Calico can actually advertise the service IP address, so the cluster service IP address on port 80 in our example, to the outside world, so that your upstream router or firewall knows where to send the traffic to. Yeah? This is often used if applications don't support NOT or load balancers at all, which still does exist. Okay, so maybe there are a few other questions. Let me see. I cannot see that from here. For one reason, I cannot see these things. Okay. What is IPVS? In terms of kube-proxy, IPVS is actually a replacement for IP tables. We'll discuss this briefly in the next slides. In two different pods with two different IP, can I to communicate? Yeah, normally, yes. You can even create a router if you would like to do that. I don't know what is meant with MP-BGP. Maybe you can clarify a little bit. Is kube-proxy needed when kubelet? I think yes. I need to check for multi-path BGP. I have no idea. You can have a pre-assigned higher port number for services. You can basically fix it. That's possible. Okay. For the multi-path, I have to check. I have no true answer for this at the moment. Okay, so how is this actually implemented? So it was one of the questions. So it was a good question. So mapping all these services to pods is actually done through kube-proxy. Now, kube-proxy, for people that are used to working with proxies, you may think that is actually a proxy daemon. It was in the very early days, but kube-proxy is actually a daemon that actually communicates with the Kubernetes masters to etcd. Whenever you define a service, there is an object inside of the Kubernetes etcd. Kube-proxy will find it out, and kube-proxy will actually use IP tables or IPVS or eBPF to actually configure that part. So kube-proxy itself is the one that actually checks the Kubernetes, and it will actually program IP tables or IPVS, yeah, which is an alternative. So every node in your Kubernetes cluster, yeah, will have kube-proxy running, yeah. So always check this, because if you don't have kube-proxy running, you have a problem. Okay. Every node also, by the way, has to have kubelet running, for that matter. So these ones are the ones actually on every node, because the programmation of IP tables on every node might be different. So kube-proxy is taking care of that. This is a slide I made a while ago. So the process is actually as follows. So once somebody defines something through kubectl, a deployment or a service, everything is always stored into etcd. Everything communicates through the kube API, and the kube API actually stores everything in etcd. So once the scheduler decides where pods need to be scheduled, for example, if I have 3 pods, and the scheduler will decide, okay, I need 1 pod on node 1, 1 on node 2, and so on and so forth. Kubelet will watch kube API etcd to actually see whether or not it should spin up a new pod. When kubelet sees that there needs to be spun up a new pod, kubelet will make sure that through the CNI interface, it will get an IP address and actually spin up that pod. You don't need kube-proxy for that. The moment you define a service, a cluster IP, well, again, this happens through the kube API. It's stored in the etcd. So it's kube-proxy that will monitor actually to see whether it has to build services. Once kube-proxy sees it has to build a service, it will pull out the information from etcd and do the necessary configuration of IP tables. So a while back, tried to figure it out. Kube-proxy, in most cases, is a pod running on Kubernetes on every node. it authenticates through means of a service account to the kube API to actually pull out that information. So kube-proxy needs specific access to the kube API to actually pull out that information. But it's interesting to see how it does it. So that means that kube-proxy needs to communicate to the master, also like kubelet. So how can you define most of the stuff? I'm using a self-built Kubernetes cluster. So you typically use kubeadmin to do that. So once you define a kubeadmin configuration file, you can actually say what the service subnet is and what the pod subnet is and the DNS domain, which is basically how these services resolve. This has to be done at cluster creation time. Okay. So these are also the values Calico will use to actually decide what pools and blocks to use. But this is done even before Calico is installed. This is something you define inside of your cluster. That's where all the Kubernetes components will go and try to find if they need a service subnet or the pod subnet. So at cluster creation time. By default, kube-proxy is configured to use IP tables. And I guess in 95% of the cases, it will always be IP tables, for sure if you create it yourself, but you can change it to IPVS. The link down here, I'm not going to spend too much time on it, but there is a comparison between IP tables and IPVS. It's mostly related to latency. What we see is, and what the blog is all about, is that IPVS only shows its relevance when we talk about more than 5 to 10,000 clusters. Then IPVS will be faster. But when we talk in the range of hundreds or 500 or even 1,000 nodes, there is no noticeable difference between IP tables and IPVS. But if you're interested, check out the link, and it's pretty detailed with graphs and so on and so forth. So service pod subnet defined at initial configuration. Once you create services, you can actually, if you want, but do not change it or do not go in there and try to change things. You can use IP table commands to actually see all the Kubernetes rules and chains that kube-proxy is building. That's also the underlying reason why at a very large number of nodes, IP tables is slower, because it creates very long IP table chains. So command is IP tables list kube services in the net table. You can actually find all the IP addresses and things to where we net and so on and so forth through this. I'll do that in a demo. I'm not going to read all this. Okay. There is also new stuff on the blog. I think it's generally available in the latest or previous version of Calico open source and enterprise, is eBPF. eBPF doesn't need kube-proxy. It's a totally different way of doing or implementing services. We'll dedicate another session to this, but just know that eBPF is a new way, a very popular way, but it also has its pros and cons, as you will see. I'm going to run quickly through these slides and then I'll jump to the demo. These are the upcoming events. As I mentioned, I think on the 19th, there is one in the Europe time zone about ingress networking. If everything works out, we'll be using Traffic for this one. There is another one on YouTube we did a few months back based on Nginx, but just for the fun, we'll take another one. So you can sign up for the events like you did for this one, of course. We also announced not that long ago the Calico certification. So you can get Calico certified for free. Just go to this link and sign up. The first people are certified. And it covers quite a lot about the networking and how to obtain it. Most things are in this new ebook we released a few weeks back, so feel free and get it. You can download it from the website or from this link for free. It's a very good technical ebook, and it will basically cover even more in depth of what we covered today. There's a typo here. Calico Enterprise basically adds more features, which we're not going to discuss today, but like DNS policies, IDS, and so on and so forth. If you need more information, feel free to reach out to us. We'll happily tell you all of the stuff or check the other webinars. If you want to play with Calico Enterprise or test it, you go to the website. There is a big try it button on front of the website, and you can actually run it in a sandbox, so you don't have to host anything if you don't want to, and you can play around with it, or you can actually link an existing Calico cluster to a managed trial. So both are available. Check it out. It's a very easy way to get an idea of what Calico Enterprise can do. So let me jump to the consoles. If I can point them.
We do have some questions, Philip, that are left over that I can't answer. Sorry, thank you.
No worries. Same problem again. Where do I find that? Okay, kube-proxy usable for node port service, even if IPVS mode is chosen. I think so, because of the NATing. I'll show you why, where the difference is, if I can find it in the demo. It actually uses netsets, which is another way to do the distribution. We'll just try to see if we can find it. Gets flushed, yes. Typically, everything is refreshed, and there are controller loops that are watching it, so if you flush it, it will rebuild. Not clear on how eBPF preserves source IP address. You can preserve source IP address with eBPF if you want, but that's basically, it works totally different, yeah. We can take this offline, but eBPF does it totally different. It's hard to explain right now, but if you want, we can take it offline. Can I use 2 HTTPS? Yes, as long as they are living on a different cluster IP, you can with a load balancer. With a load balancer, it's harder, but you can do that. Okay. Could you share the slides? Yes. Okay. Okay. So the demo is actually available here. I'll put it in the chat here. There is a link. Sorry. So the link is in the to basically reproduce what I'm going to show, so I can copy paste also. So what I'm going to do is I'm going to use a small application I use for testing. So we're going to install the application. To make my life easier, it basically executes a bunch of kubectl commands. As you can see, it basically created containers. It created services. So let me check here. You see, so if you actually do exactly the same, you don't have to run the setup command. You can actually just use kubectl, but it's easier. As you can see, there are like a bunch of backend servers, a bunch of Nginxes, and so on and so forth. It's actually a mesh of things to test. But that's not the point here. If you go to the GitHub page, you can find it. My pods are up and running, and there is also a traffic generated, so there's traffic running in that app for various testing. Okay, so we have an application. That's already something. So I'm going through the steps we discussed earlier. So I'm going to check that namespace. We're going to see the IP addresses and the labels. So this is important for services. So as you can see, everything has an IP address in the pod CIDR range of Calico running on the nodes. As you can see, everything has labels. Yeah? Some labels are assigned automatically, but you can add as much labels as you want, of course. So nothing very particular. These are the pods which we are in use. And right now, to understand, of course, services, we need to understand the concept of the labels. So right now, if I would execute this, show me all the pods that actually have a label echo server 1. So it will show me 3 pods. Yeah? That's how Kubernetes services will actually find the pods. So if I add an echo server, it will also have the label app echo server 1. The services will update it. We'll see there is a 4th one. It will actually include it as an endpoint in a service. Okay. So, for example, if I would scale this deployment, and I would do the same thing, we'll actually see that I have 5 of them. If I would go to 3, that will be removed. Okay, so dynamic number of pods, dynamic IP addresses, how is everything actually linked together? Well, as I mentioned, everything is actually linked together by means of a service. So as I can see, I already created a bunch of services, and services you can see have a selector here. So service in this case called zone 6. Basically, this is the cluster IP address here, and it groups together all the pods that do have app echo server 1. You can actually do things like kubectl or describe service, for example, zone 6, this one, the one with the echo service in and demo. You see, we can find the information. It's simple cluster IP, so no node port. You see all the endpoints here. Yeah. If you want to see more information about endpoints, I'll show you immediately. A service object can have 2 ports, like this service can have port 80 and 443. Yeah. You can see the list is not complete here, but if you, for example, do kubectl get endpoints zone 6 in the app article demo namespace, and there's a typo. See, that's why I copy paste. If you do -o YAML will probably get the entire list. So, okay. So if you scroll through this, you will actually see all the endpoints. So a service is technically not linking to a pod. Yeah. A service actually links to the endpoint. Yeah. A pod has more information than an endpoint. So that's what kube-proxy is actually looking for in etcd, which are the names, which are the endpoints from zone 1, which is the name of zone 6 for the name of the service in etcd. Yeah, that's what it's actually doing. So we already described it. So how can we access it? So for example, if you want to play around and make sure it works, we can, for example, run, this is my testing container, so you can use anything if you don't trust this. So we can actually run a test container, and then we can do something like, for example, yeah, and it should work. This is what the backend application is doing. So you can see, there are multiple apps on it and so on and so forth. So you can see, I can simply connect to zone 1. Zone 1 is actually the service name. Yeah. I can actually change it to another zone, and I can go to zone 2. Yeah. Remember, I could actually do dot namespace, dot service, dot cluster, dot local from any namespace. This is how applications or microservices connect to other microservices. They don't need the IP address. They don't need the IP address of the service. They can just actually connect to a logical name, which is resolvable by DNS. If you want to know this, you can actually do this if you're interested. So you can actually see this is the DNS name or the prefixes. So you can actually do something like, so 6 in, for example. Yeah. And that should also work. Yeah. So that's how it actually works. And the fact that you have this, you can see the namespace is in the DNS name. So that means that from namespace X to, in this case, uproutable demo, it's resolvable and reachable. Yeah. So if you want to see all the gory details on IP tables, well, you can also do this. So if you execute this command, you actually see all the tables, which is, of course, a little bit long, but if you're interested, you can go and figure it all out. But I'll give you a hint. Yeah. So if you execute this one, show me the IP tables list, kube services. Yeah, you can actually see all the services that were just created. Yeah. Let me highlight, for example, zone 1. You can see there are a few rules, but the most important one is this one. You see, if something connects to the service IP address here, yeah, doing things that I should not do apparently. Yeah, so if I connect to the service IP address, yeah, I'm actually going to this chain. Yeah, so if I'm going to this chain, I can actually go and try to see what's happening in that chain. So I need to change the name, of course. So if I hit that IP address, I get destination mapping to whatever is in this chain. Yeah. is something is so slow. You see, so if I match this rule, I get actually knotted to this rule, yeah. And actually the factor is SEP. I don't know what it's sent for, but actually if we'll take a look at that chain, you can actually see all the endpoints. So let me do this. You see, and this is finally the pod IP address. Yeah. So if I would do it for zone 6, you would actually see 5 of them. Okay. This is how it works. So you basically hit a few IP table rules. Yeah. The first one is actually sending you from that virtual IP address to actually a group, yeah, and that group basically does the DNATing to all the pods. Yeah, so there are a few rules. So if you want to follow the chain, there are like 3-4 rules. I'm going to, for the sake of the demo, do we have time left? Not really, but let me do this for zone 6. Yeah. So this is the one for zone 6. Yeah. So let me see if we can find that one quickly. There's one thing I want to show you. You see, if we take the one for zone 6, you see that for the service definition, there are like, I scale it up, so 5 ones. Yeah, and here you see the statistic mode random probability, which is actually how IP tables implements the load balancing. If you figure it out, it basically says that you have about 20% chance to hit this rule. And from the other rules, you have 25, 50, 30. So at the end of the day, if you make the calculation, you see the last one is 50% chance between 2. So that means that the traffic is distributed equally. And these are the chains that are actually updated when you do scale up or scale down. So if you look in detail for this one, for example, you'll probably find the information about which pod this rule is referencing to, you see. If we'll take another, you actually see that it's probably another IP address of this one. You see, that's another one on another node even. Yeah. So this is how this all works. Pretty complex. Luckily for us, we only have to define a cluster IP and a pod and a network policy object in the future. But at the end of the day, it's all implemented by kube-proxy in IP tables. This is the part which is typically different when you use IPVS. Yeah, IPVS is a way more advanced load balancer for that matter. Okay. To conclude this, if you want to, so we are using, in this case, we are using cluster IP addresses. If you want to update it to a node port, you can. So you see the type node port here. And if you want to see the details, well, you can actually go in IP tables again. You will see that there is an other list that is actually mapping these port numbers. So even if you use node ports, it's doing even more reprocessing. But that's how it is designed. Everything is in the link I provided. You can actually try to reproduce it fairly easily. That's it for me. I don't know if there are any questions left. Let me see.
Just two more.
Two more. So basically nothing to pods using it. It's not kube-proxy that is doing it. Yeah. So it's not the pod itself, it's IP tables that is actually doing the destination, nothing. It's kube-proxy that configures IP tables. What does the endpoint IP address CIDR range get? It's from the pod subnet. So the endpoints are actually pods. It's an IP address of the pods. Yeah. There are no more questions. I thank you. Thanks for joining that early in the year. I hope it was interesting. If you have any other questions, feel free to Twitter, LinkedIn, or join us on Slack, and we'll give you more information once we can. Thanks. Hope to see you in 2 weeks when we talk about Ingress, which is basically more advanced topic based on load balancing. Thank you. See you soon. Hope it was interesting. Cheers. Bye.